In dynamic design or motion, it's possible to have somewhat adaptive inputs to forces and motions. In order to do that, it's necessary to use markers. We're going to look at this assembly where we have the two blocks, and the first block is grounded. The second one has an axial align constraint and then a planar align constraint. So it's allowed to translate in the direction of this axis for that hole. So this acts like a prismatic joint. And now we'll demonstrate functions using this assembly. So we'll create a new mechanism and use the automatic assignment for the moving and grounded parts. So here's the prismatic joint that was automatically created, and we're going to add a force, and this is an action only force, so this is just going to be a force on the second block. Okay, and its direction is relative to ground, so it's a constant direction, and we'll just let the force act at the center of this circle, and the direction will be the direction of that. So you can see it's pointing down. We can flip it here, and now it's pointing up. Okay, and the function for that force, we're going to use an expression. And to find out what expressions are possible, you can visit the help information. So just press F1 on the keyboard, and we'll come up. I guess maybe I need to cancel this first. Okay, cancel that. F1 should bring up help, but it does not. So instead we'll just right click on motion model, go down to help, and you can see all the different help topics. We want to use functions and expressions, but that's not quite right either. So we're going to go to supported functions. Okay, so these are the functions that we can use in our expressions. So we've got these mathematical functions: square root, cosine, log. We can get the simulation time to use in our expressions. And then we have expressions that are dependent on markers. And markers are coordinate systems that are created with joints. And we can use in our expression, for example, the rotational displacement of that marker, or the translational displacement of that marker. And so in this case, we're going to look at the translational displacement. So that would be dz, the translational displacement in the z direction. So this joint, the z direction is up and down, so that's the motion. So dz is a translational displacement in the z direction. And if we want to find the z displacement for a marker, this is the syntax we use. We would say dz I, and I is the marker number, and we'll see how to find that in just a second. And then these values here in the brackets, those are optional. So we can have, by default, the displacement will be relative to the world origin, but we can have it relative to another marker, and that would just be a second argument to this function. And if we want it in a different direction, then we could have a third argument, so the marker for the direction that we're interested in. So we're just going to use a single argument because we're okay with the direction and the world origin. So we're back to our motion, or our force that we wanted to create. So we want to add a force, an action only force, and this is going to be relative to ground. Again, the location, go through this in the direction, and it's pointing down, so we'll flip it. And the function is going to be an expression. So we want dz, the displacement in the z direction. Now to get the marker number, we click this triad, I believe it's called, and we can find the parts that we want. So block 2 has this marker, and but what we wanted was for the planar joint, excuse me, so it's marker 3. So let me just delete this number here, and now we get the marker for that joint. Okay, so DZ3. And we want this, so this is, we're going to pretty much make a proportional controller. So we want the force to be proportional to the difference between 550 millimeters and the current position, the Z direction. So we want to move this thing up. This is a proportional controller to get it to move to 550. Say OK, and zoom out a little bit, and run the simulation. So you can see that it just oscillates around 550 millimeters. So that's because this is an undamped system. There's no friction in the system, and so it's going to oscillate forever. So let's add a damper to the system, and it's a translational damper. And the first component, the second component, and it will be in the direction along that axis. And we'll go ahead and provide a damping coefficient of 0.05. Say OK. And now rerun our simulation to see the difference. So now you can see that we have this underdamped system where the oscillations die out. And the main points of this video are to show using markers and how they can be used in expressions for applying motions or forces to your mechanism.